meaning after this session, we go all upstairs where the Penrose tilings are at the entrance, and there'll be a conference photo that Peter will administer, and then there'll be a video with a drone that Adi will administer. So it'll be very exciting. So please all then go upstairs, follow basically the locals.
Welcome back for the afternoon session. We now have Meng Cheng from Yale University, who will tell us all how we can stop worrying about decoherence.
Okay, thank the organizers for putting up this really exciting conference and inviting me to speak. So, as you can see, the talk is about how I learned to worry about decoherence and love mixed states. Of course, that's because I don't actually work on quantum computing. I don't have to worry about decoherence. But our series is about a story about basis, but in an open quantum system. And before I get into the physics, let me acknowledge my collaborators. So this is the stuff that I'm going to talk about is done in collaborations. Leo, who's a graduate student in Parameter, Chong Wang, and Tyler. And also Kurt, who's local, well, who's in London, probably not local, and Tabor. And I'm also grateful for many discussions with many colleagues on these topics. All right, and everyone's very happy on the pictures. All right, so here's a quick outline. So I'll first define the problem, why I think this is an interesting problem to consider, and then I'll discuss basically two examples. I'm not going to tell you a general story because we don't have a general story yet. Two examples that are intrinsically mixed, something you cannot get in the world of ground states. Okay? And I also want to justify why this is a talk appropriate for this conference, because everything I think I understand about this problem, come from generalized symmetry or emergent symmetry. So somehow this is the only handle that I know how to put my hands on the problem. Okay. So two examples. The first one is a 1D system, 1 + 1 dimension, a topological order in 1D. And then I'll talk about a thermally stable topological state in 3D. Okay. And then there's a story in 2 dimensions. So you should check out a poster by Abhinav, and then also a paper from a few months ago. Okay. All right, so here's some motivation for why we should at least think about mixed state, because of course there's this beautiful theory of topological order states as ground states of gap Hamiltonians. But as we talk about ground states, obviously it is only for a closed system. Okay. And then you have pure states, or a system that's well isolated from the environment. Of course, that's not what you actually have. The system, whatever system you have, is constantly interacting with the environment, is disturbed by the rest of the universe. So the reality is that you always have mixed states. You always have quantum states in open system, which are described by mixed states. All right. So then it comes a natural question as how to sort of extend our knowledge about topological order or phase of matter in the ground state to this more general setup of mixed states. It's been a very popular topic. So this is a partial list of what has happened mostly in the past couple of years. All right, so let me now first review how we define phase of matter in pure states, in ground states mostly. So first, which states are we talking about? Okay. So we're talking about in that context, we're talking about ground states of local Hamiltonian with a gap. Okay. And the gap guarantees that the correlation functions of local operators are exponentially decaying. So that's a feature of gap states. Okay. And this is sort of the states that we are interested in when we talk about ground states or talk about topological order. If we want to speak about phase of matter, there has to be equivalence relation between different states. So phases are equivalence classes of states. And the natural equivalent relation for ground state phase of matter is, in the quantum information sort of language, is a finite depth quantum circuit. A little more precisely, quasi-local circuit. So let's not worry too much about the difference between quasi-local versus finite depths. And it's basically a kind of a convenient tool to talk about evolving system with a local Hamiltonian for a finite amount of time. Okay. So if you can change one state to another by evolving with Hamiltonian for some finite amount of time, they are considered equivalent. So that's a kind of the extent of this definition. So under this definition, the kind of states with, which are ground states of gap Hamiltonian can be grouped into different phases. And if you want to go from one phase to another, you have to cross a phase transition. So that's this schematic sort of phase diagram that we have. There's a trivial phase, which is represented by the trivial product state. Okay, so now let's try to take this to the setup of mixed state. Okay, so mixed state basically arises because the system is inevitably coupled to environment. Of course, we know very well that there are these thermal states. At finite temperature, these are mixed states, most familiar mixed states. And there are other kinds of states. You can have a state evolved under some sort of dissipative evolution, coupled to some noise, under some decoherence, you get a mixed state. Or it can be steady state of dissipative or Lindebladian evolution. Okay. There are all kinds of which you can get mixed state. Okay, so again, we need to sort of define what states we want to consider and what sort of equivalence relations in order to have a problem of phase matter to study. So first, let me introduce this notion of a quasi-local quantum channel. So this is a sort of a natural generalization of time evolution for a closed system. It's basically a time evolution open system. For more formally, it's defined as follows. So quantum channels are maps between mixed states. It maps a mixed state to another mixed state. Okay. Now, a quasi-local quantum channel is composed of the three steps. So first of all, we introduce some ancilla. Okay. The ancilla is a model of the environment. And then we apply a quantum quasi-local unitary that potentially couples the system with the environment. So this is modeling the interaction between the system and environment for some finite amount of time. And then we get rid of or tracing out the ancilla. And the result is applied to the system. And the fact that we have a quasi-local channel here means the fact that we have a quasi-local unitary here means the channel is quasi-local. Okay. So this is basically a model of a dissipative evolution in an open quantum system. All right. Okay, so now let me talk about what states I want to consider. I'm not claiming this is everything they want to consider, at least there's a working definition for this talk, is that I want to study mixed states which can be obtained from the ground state of some Hamiltonian, okay, by a quasi-local quantum channel. So you can purify it into a ground state of some Hamiltonian. And they should have short-range correlation. So it behaves as if there's a gap. Of course, there's no gap for open quantum system, but correlation functions are exponentially decaying. There's some more technical conditions about strong to weak symmetry breaking, but no, let's not worry about that too much. So this is a class of state that I want to consider, and I also need to, yes?
Just a question to clarify. So here you want the exponential decay.
Yeah, I want the exponential decay, yes. Right. Also goes to 0, but I also want the exponential decay. So I also need to tell you what the equivalent relation now for the mixed states. And here comes a big difference, or a significant difference. And that's because the unitary evolution is invertible, right? You can evolve by unitary operator U and evolve back by U dagger. However, dissipative evolution is not invertible in general. It's not reversible. So just having a one-way evolution is not enough. Therefore, we need to demand the equivalence, or the equivalence defined by having dissipative evolutions connecting two states in both directions. So more precisely, these two states are considered equivalent if you have two quantum channels, quasi-local quantum channels, that goes from rho 1 to rho 2, and then come back, rho 2 and rho 1. Okay? And these two channels are generally different. So we demand this kind of two-way connectivity by quasi-local quantum channel as a definition of an equivalence relation. Okay, and imagine under this equivalence relation you get some sort of a space of states divided into different regions. States inside of one region in the same region are connected in both directions by quasi-local quantum channels. All right, so this is set up, and now we can start asking what are the possible phases of matter, etc. Okay. So again, let me emphasize that two-way connectedness is really essential because it's really easy to mess up a quantum state. You can turn into a quantum state, whatever quantum state, infinite temperature trivial state by applying a depolarizing noise, or a swap gate, a swap channel that swaps the system with a trivial environment. Okay, you can always do that, but it doesn't mean that you can go back. Okay, so it's easy to mess up things. That's the second law of thermodynamics, but to recover from the noise is a non-trivial question. You can also show by this definition that any invertible state, invertible pure state, is actually two-way connected to a trivial state. So there's no natural notion of an invertible topological order for mixed states. Okay. All right. Okay, so now we have a question that's defined. We have a class of mixed states that we want to study. We have equivalent relations. So how are we going to approach the problem? Well, one way to approach the problem is to think about the symmetries. Here's another sort of interesting point about mixed state, is that there are two kinds of symmetries that we should pay attention to. So there's a weak symmetry, which actually doesn't play a role in the rest of the talk. So let me skip directly to strong symmetry. The strong symmetry is the one that acts in somewhat weird way. So rho is a mixed state, and W is some unitary transformation. So I'm going to just talk about invertible symmetries in this talk. And we apply W to one side of the density matrix, and you get a phase vector. It means that if you have a decomposition of the density matrix into pure state, then each one of them has to have the same eigenvalue under this symmetry transformation. Okay. Although it's called strong symmetry, it's actually a very familiar concept in STEMAC. This is basically a symmetry of a canonical ensemble. So remember, canonical ensemble is when you have a system coupled to a mass, the number of a particle in the system is conserved. So if you measure the particle by applying this W, well, you're going to get exactly the same phase vector, because every state in the canonical ensemble has the same number of particles. All right.
I have a question.
Yeah.
Is there a way to distinguish between weak symmetry and strong symmetry by looking at their defects? Or is it something totally beyond the defect picture?
I don't think it's beyond the defect picture, so maybe I'll get to that in a couple of slides. I'm not going to talk about defects too much, but no. We do have to use, for example, knowledge about anomaly. Okay, so it's called strong symmetry, and there's a good reason, because as Sal just pointed out, the strong symmetry actually knows about all these projective phase vectors, which are the hallmark of anomaly. And if you have a convex sum, a probabilistic mixture of states having a strong symmetry, then each one of them has to have a strong symmetry. Okay. And if you have a quantum channel, if you have a state obtained from another state by a quantum channel, and the state itself has a strong symmetry, and then its parent state also have to have a strong symmetry, so you can kind of push the strong symmetry over a quantum channel. So it's a very invariant that you can use to classify states under the actual quantum channels. So that's why it's actually very useful. All right. Okay. I guess I don't really need to tell this audience why we want to think about generalized global symmetry. There are many kinds of generalizations, and we also learned many structures to symmetry more than like the group structure. There's all of these higher structures in defects, anomalies. Especially, the global symmetry has anomaly, two-fold anomaly, which is obstruction to having a trivial symmetric state. That's for pure states. Okay, and I'll only talk about invertible symmetries, even though I think everything I said has some sort of generalization to non-invertible symmetries, but let me stick to invertible symmetries. All right, so the first example I want to discuss is a one-dimensional spin chain, a state in the one-dimensional spin chain. And the kind of philosophy I'm taking now is that let's just look at the states. Let's not worry about where the state comes from and how do I actually build this state. The states that I talk about here, they do have very physical origins. There's a way to sort of construct a state physically, but let me focus. Okay. So first, let me just define the symmetry. Again, I'm sure that for this audience, this is familiar. So the system is just a chain of qubits, okay, or Ising spins. And the non-anomalous Z2 symmetry is a product of Pauli X operator. So this is X is a Pauli X. And you can make anomalous by multiply this Pauli X with the CZ, the product of CZ gates on each neighboring pair of spins. Okay. And then this new symmetry is still Z2, U squared is 1. If you put a chain on with a periodic boundary condition, but now it's anomalous. Okay. All right, so now let me build a state which has this strong symmetry. First, if you want to build a pure state with a strong symmetry, then we know it has to be somewhat non-trivial. Right? It has to be gapless or it has to spontaneous break symmetry. But now there's a different possibility for a mixed state. So I can write down a mixed state with this strong symmetry, and the mixed state literally just takes this form, 1 plus u. So 1's identity and u is that symmetry operator I defined earlier. And 1 plus u is basically the projector into a subspace with u equals 1 eigenvalue. So it's a projector into the subspace, and rho is a maximum mixed state within that subspace. And you can convince yourself that this state is complete featureless. If you measure any 2-point function, 3-point function of local operators, it comes out to be 0. Okay, so there's no feature state. It looks very boring, but just from the fact that it has a strong anomalous symmetry, we can immediately conclude that it cannot be equivalent under this kind of two-way connectedness to a trivial state, because as I just mentioned a couple of slides ago, a strong symmetry is like a very infectious disease. It's propagating everywhere. So if you can get this state from a product state, from another state by a quantum channel, quasi-local channel, then this state also has to have a strong symmetry. Also, it's kind of complicated by the purification of the channel. But you also get a U tilde with the same anomaly that follows for the locality of the channel. And this state has to have a symmetry. But we know U has a anomaly, so is U tilde. So this state cannot be a product state. Okay? So this rho plus cannot be equivalent to a product state. So it's a non-trivial state, a non-trivial mixed state. And we can even make a stronger statement that not only it's not equivalent to a product state, it's actually not two-way equivalent, two-way connected to any quantum state, pure quantum state. Okay. So it's really intrinsically mixed. There's no analog of this. There's no equivalent. There's no counterpart of this in the world of pure state. Okay. All right. To explain that, I need to discuss the following property of the mixed state, which is called the multipartite separability. So this is sort of the precise definition of what it means for a state to be a tensor product. For pure state, we know what tensor product means. A natural generalization of that idea of tensor product to mixed state is this concept of separability. So if a state, if you have a bipartition of a system into subsystems A and B, and then the state is called bipartite separable, if you can write it as a convex sum, a mixture of tensor product states. So P is some probability, and these rules are density matrices defined on the subsystem. And similarly, you can define tripartite separability or any number of bipartite. So we can ask whether the state is bipartite separable, more or less asking whether you can kind of factorize it into two states. All right, so here's a theorem we proved that rho plus, the state that I just defined on the previous slide, is bipartite separable, meaning that you can write it as a tensor product of states, a mixture of tensor product of two density matrices on subsystems. For this particular bipartition, has to be this particular tripartition. You cannot do this. It's not possible to write it. It's not tripartite separable for this tripartition. Okay. And there's a kind of a strengthening of this theorem that you cannot even do it with a quantum channel. But this is the key to the argument that the state is not equivalent to any pure quantum state, because this is impossible for a pure state. If a pure state is separable or a tensor product for any bipartition, then it's also separable for any tripartition. So this is the kind of a very strong difference, very big difference between this particular mixed state and a pure state. So this is not possible for a pure state, therefore this state is not two-way connected to any pure state. All right. Here's an outline of proof, but in the interest of time, I'll skip the proof. I'm happy to explain it if anyone's interested. And just to sort of fit into this event, I want to give a picture of what's happening. It's actually sort of enlightening. So to construct this state, let's start from double semyon, the disk of double semyon state. So I'm drawing spatial pictures. These are like spatial space-time. So start from double semyon, and we choose a topological boundary condition. There's only one. So you choose that one. And then, well, this is not a 1D system yet. So we make it 1D system. The most obvious thing you can do is just to trace out part of the disk, trace out the inner disk, and now we're left with a strip or annulus. So I claim that this is exactly the state I discussed on the previous slide. By tracing out the inner disk, I get exactly this rho plus state. Okay. So it also gives you a purification of the state, which is a 2D system. You cannot purify it into a 1D system with with gap, but no, you can purify it into a 2D gap state. Yeah. All right. Okay, so I think I have to speed up a little bit. Although I do have a lot of slides, but I think there's a simple conclusion I can tell. So now I want to turn to another class of mixed states, which are the more familiar ones. I haven't really explained to you how to get this 1 plus u, but I don't have to explain why thermal states are interesting. Right? Just finite temperature states. Okay. So now that there's a non-trivial thermal state, non-trivial in the sense that I defined earlier, in 3 dimensions. But let me just give you a little bit of a background of the thermal stability of topological order states. Okay. So here, the topological order refers to the usual sense of topological order. You have some Hamiltonian, the ground state topological ordered, and then there's a very natural question of what happens if you raise the temperature. Does the thermal excitations completely destroy the state or not? It's also related, although not exactly equal, to the question of self-correcting quantum memory, which I think you heard about from Potion yesterday. So there are a few things that we know about these kind of thermal stability of topological order states. So in 2 dimensions, nothing's, as far as we know, nothing's thermally stable. If you raise, say, toric code to a finite temperature, it's trivial. Okay. In a sense I discussed. This was proved by Matt Hastings. And consistent with that, there's no self-correcting quantum memory in 2 dimensions, as far as. Now, if you allow me to go to 4 dimensions, then we know there is a thermally stable topological order. That's a 2-form toric code, 2-form Z2 toric code. And the reason that it only has loop excitations, which are somewhat expensive to create at finite temperature. And this state can be used as a self-correcting quantum memory. So you have self-correcting quantum memory in 4 dimensions. So what about 3D? 3D, you have topological ordered states with loop excitations, but with also particle excitations. So usually the idea that the particle excitations ruin your state at finite temperature because it doesn't really cost anything, just a finite energy gap to create a particle at finite temperature. And once you have some of them, it kind of destroys everything. So that's a usual sort of intuition, but we actually, when we examine this question carefully, there's a different answer. So let me just say what happens in 3D. So the questions, are there any non-trivial phases at finite temperature? And, well, there's no known self-creating quantum memory, but let me get to the bottom line. So, well, let's skip this and maybe just skip to this model. So I'm sure this is a model familiar to many of you. It's a 3D fermionic Tauri code. It's a bosonic system. The system poly-spins, qubits, sorry. But it has a Z2 gauge theory as a TKFT with a fermionic quadratic particle. So you can write down the Hamiltonian of this model. It consists of this vertex term, there's Paquet terms. The details are not terribly important. And this model has two kinds of higher form symmetry. So corresponding to the loops, there are these one form symmetry defined on surface operators, which is non-anomalous. But there's a Z2 two-form symmetry, which correspond to the fermion particles, and that's anomalous because of fermionic statistics. Okay. All right. So what happens at finite temperature? Well, this is schematic sort of plot of what happens. So at 0 temperature, you have this beautiful topological order state, which can be used as a quantum memory. Once you go to finite temperature, it's not quantum memory anymore. It becomes a classical memory. And then if you even raise the temperature even higher, then there's no memory at all. Okay. So the real question here is whether this region is non-trivial or not. So what's really this region? Okay. Well, so I guess I'll have to just jump to the conclusion and explain the basic idea behind this conclusion. So this is another theorem that essentially below certain temperature, this temperature is below Tc, this state is actually topologically non-trivial in the sense that it's not equivalent to a trivial product state. And the idea, so at the finite temperature, you have both excitations. I'll wrap up in 1 minute. You have two kinds of excitations, the particles and loops. Okay. The particles are just there and they are everywhere. We cannot do anything about particles, but we can do something about loops. It turns out that we can clean up the loops by a quasi-local quantum channel to get to a state which is not really a thermal state anymore. It's more like a state with all the particles proliferated everywhere. Okay. This state has no loops, has fermions, and it has exact anomalous two-form symmetry. So the key here is that the two-form symmetry is anomalous, and we can clean up the loops to make the state strongly symmetric under the anomalous two-form symmetry. And then just from the anomaly, you can know that it's not a trivial state. So from this argument, we can conclude that this finite temperature state belongs to a non-trivial phase for any temperature below that threshold, T0. We can calculate T0 as some number, 2 over log 6. So there's a whole region of temperature where this thermal state is topologically non-trivial. Okay, so I guess I'll conclude. So we have, there's a definition of, there's a problem of what are the mixed state phases with equivalence defined by two-way quasi-local quantum channels. And wait, I haven't got to the, and I gave you a couple of examples of intrinsically mixed states. They're all kind of understood, at least for me, from emergent symmetries. And it seems like strong generalized symmetry could be a very useful kind of guiding principle to think about phase of matter, not just in the ground state, but also in mixed states. Okay. Thank you for attention.
So thank you, Meng Cheng, for this nice talk. Questions? Yeah.
So you choose double semi. What's wrong with the toric code or other?
That's trivial. That state is trivial.
Everything else is trivial?
No, not everything else. I mean, if you do the same thing with a toric code, you get a trivial state. Because the symmetry is not anomalous. I don't know.
Just to make sure I understand, so for the thermally stable topological order in 3D, there you need this two-form symmetry to be exact on the lattice? Meaning if you perturb the lattice model a little bit by breaking that symmetry, then the thermal state is no longer non-trivial?
So we don't have to require the symmetry to be exact. It could be approximate. I mean, you can perturb the Hamiltonian, and then there will still be an emergent anomalous two-form symmetry, and that's good enough.
I see.
The key point is that you can clean up the loops to a state with only particles.
So for non-mixed topological states, usually we say there's some edge physics or whatever. So here, for these mixed states, even though they're topologically non-trivial, I understand the correlation function in the bulk is still exponentially decaying. So what are the exotic physical consequences of the topological order?
Yeah, so that's a good question. So in a lot of these cases, you have, for example, degeneracy on a torus, right, on some manifold, non-trivial manifold. That, in some example, you still have that in the mixed state topological order.
Degeneracy of mixed state.
So yeah, okay. So degeneracy, of course, we shouldn't really talk about degeneracy because there's no Hamiltonian, but we can talk about the space of locally indistinguishable states. That's still well defined, and then we can put some structure on that state. So sometimes it's just the locally indistinguishable state, they form a convex set of density matrices. Mm-hmm. So in some cases, just a few points on the extremal set of the space is a few points, then it's classical, but sometimes it's a continuum, then it's a quantum memory.
You see, so here you still can tunnel fermions around.
Although here,
cycles.
For this fermionic state, the fermionic toric code, it's not a quantum memory. So right now, in both examples, actually, so all we know that these are non-trivial states, but we do not know exactly how to sort of characterize it. We can show that they are not equivalent to trivial states, but we don't quite understand how to characterize these states more than just saying they are not trivial.
Okay, thank you.
A very similar question to the previous question is, could you also show that this 1D state is not two-way connected to a pure state by considering it on open boundary conditions?
I think so. I think you can do that too, right? And the anomaly will tell you that there's something. If you have an anomaly on an open system, well, on an open chain, then the system has to have long-range correlation, and that basically contradicts the fact that you have bipartite separation.
We don't have time for more questions, so yeah, let's thank Meng Cheng again.